So okay, we start with the opening the system identification toolbox that you already have here in your in the description of your chemical process design and oriented to the synthesis of your controller. And we already shown in the previous part of the movie, as you can see here in the second part, how you can derive the PID controller with an automatic feature, so using the auto-tuning approach. And if you remember, so we will show it later, that it allowed to obtain quite limited results, so poor, at least by inspecting the output compared with the controlled output. So we will see in a while. So I'm recalling here the system identification toolbox that you can open it to re-upload if you remember. So we can open the previous session. So an advantage of the system identification toolbox is that you can save your previous work, and in this case we open the file model for control design.sid. So if you remember, the extension of the file SID indicates that this is a file generated by the system identification toolbox. So open it. And so I don't want to, okay. And if you remember, we selected as at least as a best, let's say, best model, this one, the ARX331, because we already discussed that perhaps it represented the best trade-off between complexity and prediction or simulation feature, efficacy, effectiveness. So we can take this model ARX331 and then we can drag and drop to the block here, to the rectangular 2 workspace. So you can have it here. And of course we need to call again this file, syspress open. If you remember, just use, because it generates the data that are used for the simulations. So this is just want to remove the instruction, the beginning clear all, because it removes everything in the workspace. So I leave just close all and CLC. So I run it. Okay, so we don't need this picture, if you remember, because we just need and with the Simulink, we open the file. It is here. No, sorry, is here. The previous is not the final one. It's just the working file that we generated. But if you look in the we can see it later at the end of this module. You can find everything in your file. So it's already available, everything. I just want to show you the single steps that we. Just a second, because it takes some time here, because I have other programs running and. So we can close the system identification toolbox. We don't need it. And here, so we can find, if you remember, so again, the PID controller, okay, you know, if you remember that it had very limited, and I want to repeat the design, so we can starting from the RX model. We open the library and we go to the model predictive control toolbox, and you find the simple MPC is the first block that we are using here. So of course you need to have installed the model predictive control toolbox. So check if you installed all the toolboxes that you need. Okay, and we put it here. And before connecting it, if you remember, normally this block has 3 inputs, and the model output, which is used here for connecting the feedback, and the reference, which is we are using the reference as the output, the real output that should be followed by the system, tracked by the system with the control. And there is a further input that we are using later, which is a measured disturbance. So it means that it is represented by the equation error that we are generating with the recursively square approach. So, but in this time, just click on the block and in the main mask disable. You can see here, you can add other inputs. We can comment it later. So we can remove the measured disturbance because at the moment we are assuming that is not available. So apply, okay. And in fact now we are connecting the model output here and the reference. So this is the setup of our system. Of course, we need to connect. Okay, sorry, because I prefer to have the feedback on the lower part. Okay, so this is the scheme. So you have the model predictive control, and as you notice, the input of this controller is different because it's assuming that the controlled output, or at least the control scheme, is not very simply as for the previous PID situation. A function of the error is something more complicated. So, but let's go into this block, and of course here is empty because you will have it at the end of the design, and we can go in the button here, design. Let's see if it's working, because the last time it wasn't. It sent a strange message. Now he's trying to optimize everything. Okay. This is the window that is automatically pop up, and we go. It's still working. Okay, we click on the MPC structure, and if you can see here, it is summarizing the inputs and the outputs. So please define here the sampling time, which is 5 seconds, is a variable that is defined in the if you remember by the problem. And so we confirm that the manipulated variable is selected, and the measured output is the only one signals that are used. So import So here, just define the 5 seconds here and select the 2 inputs and outputs. So 1 input and 1 output that is used in the model. So you don't need to change anything here in the other options. So import. Let's see if it's working. Let me check if it's still okay. Is compiling, and then if you see here, okay, is so we have, as you can see here, the model is it was, so we can close it here. Okay, now we have here the picture of the input, so the output of the controller, and here the simulated output. So in principle, very briefly, this block try to optimize an input for the process in order to have that the simulated output of the system is very close to the reference. So let's check to the part of the tuning. As you can see here, we have the sample time of 5 seconds, and we can is something that can be defined, set in a practical case. So a prediction horizon of 15 seconds and a control horizon of 10 seconds. And then you can try, as you can see here, so the sample time is 5, the prediction horizon is 15, and the control horizon is 10. So what does it mean? What does this parameter mean? So it means that this block, so in very simple words, this block tries to optimize this control, which is the input to the process, in order to have the output of your process following the reference output. So we can play here with, for example, in order to, as you can see here, if you improve the control loop performance, as you can see here, if you have, like in this case, you can see that your control output is almost going to the reference in a faster way if, for example, you are asking to your controller to be more aggressive. But pay attention, because as you notice, while your controller becomes too aggressive, as you can see here, that the input of your process is very high. And if you remember, the output, so the input of your controller was at maximum, the maximum value was 100. So it means that perhaps the choice of the control loop performance to be too aggressive is not the best choice. So you can reduce, for example, the closed loop performance in order to have like a trade-off. As you can see here, you have a maximum of your input about 100, which is the maximum allowed. The physical limit for your process. And you can try something, perhaps, if you want to move this other slider, but it seems that it doesn't change anything. So we can leave, and perhaps as a trial, let's try to keep here, for example. To me, is the best value, as you can see here. So the controller This is the output of the controller, and I think is the best choice because as you can notice here, the output doesn't exceed the physical value of 100. So to me it represents a trade-off, the optimal trade-off between the robustness. Robustness, if you remember, if you move the slider here, it becomes more robust, but you can see here the output of the process is lower. On the other hand, if you improve the aggressiveness of your process, also the process is behaving faster. So again, we can try, as in this case, I try to choose, for example, this value. So is something that you need to try. It's like a trial and error procedure. The only thing that you need to define in this when you want to use this block is that you need to define the sample time of 5 of course it is a parameter of your design, of your project, so it's something defined. And normally the prediction horizon means that how many seconds you are going ahead in your simulation when the control is applied. So the idea of the model predictive control is, in this case, is to generate 10 seconds of control in order to optimize the output of 15 seconds. So it's something that, as you can see here, that is very powerful. We will see later in our simulation. There is another another something parameter that perhaps you can decide to use is here, this button constraints. If you click on constraints, you can define, in a while, you can define the input and output constraints. Well, we don't have any constraint in the output, but in the input, if you remember, the opening of the valve was opening between 0 and 100. So it's something that you can include. It's very interesting because you can include this constraint in the design of your parameter, of your controller. So you are sure that the output of the controller doesn't exceed these physical limits. So we can put here 0 and the maximum is 100. I don't know if this is clear. Since the output of the controller should represent a physical variable, and this physical variable varies between 0 and 100, so we can include this limit, this physical limit, in the design of our controller. So it's something, is a feature that can be used when you are designing this controller. It's very powerful. We don't just notice, just a remark. You can, for example, define how fast your input has to change. Well, in this case, we don't have any limitation, but in some physical plants, you can include this input. For example, when you are controlling wind turbines, there is a maximum value of the speed that you can use for modifying the pitch of the blade. So it's something very, very powerful. So in this case, I just modify the input, so in between 0 and 100, so apply, okay. So these constraints is included in your design now, and perhaps you can see if you can try. Now, as you can see here, the input is saturated because it's taking into account this physical limitation. So it's not exceeding 100. But I think it's better not to use a too aggressive controller. So we can, for example, again, using this, I don't want to use a too aggressive controller. And once you have generated this controller, you can also use decide to save this controller or export. So you can update the block if you choose to update the block. So the block is the parameters of your controller are included in an automatic way in your Simulink block. So let's select this option, and then we check the simulation with the real data. So let's see what happens. And now we have the controller. Perhaps depending on the fine-tuning of your controller, you can obtain different results for your controller. So let's try to simulate. And as you can see here, this was the performance of your PID controller. Let's compare. As you remember, the performances of your PID controller were not very interesting. It's not working. But if you notice, from the normalized minimum square error, it is decreased by 1 order of magnitude. So it means that model predictive controller improves the performances of your controller. And if we check as you can see here, the output of your control system in blue is following quite nicely the output, the reference, which is in the yellow. So it means that the model predictive controller is able to improve the performances of your system. So I don't know if you have any question, but this is one. This is represent how we can use this controller for regulating our system. Of course, our task is not concluded here, but this is just an intermediate step, because after that we should apply our process to generate the data for our is something that we will see in the next lectures, but we will use this controller as a reference. If you remember, the meaning of the reference model is something that the neural network we use to learn how to behave when the neural network will be applied to the real system. So let's see now another intermediate step. So let's copy and paste again this block here. I'm going to remove this model predictive controller, and now connecting the output here. Okay, and now I want to show you another design of model predictive controller, which includes the estimation of the disturbance. So let's take from the library the model predictive controller in this form. So we are connecting the model output again, the reference as in the previous case, and now we are exploiting the disturbance. So we are using this input, which is a disturbance that is generated by your system. How we can generate the disturbance, the model of the disturbance? So I'm going to take from the system identification toolbox. Let's go and take the estimators, and we are going to take a block that you already know, which is the recursively square estimator. If you remember, we saw this recursively square estimator is the recursively square with forgetting factor that can be used for the estimation of your equation error. So let's use this block here. Let me see if I can do it here. So now I included this block here. I don't know if you need, of course, to have installed the system identification toolbox. And I put this block here. So now the most important part, as you remember, when you are designing your system identificator, the recursively square, is the selection of the regressors. So how many regressors do we select? So in order to select the regressor, let's check which is the order of the model that we selected. The order of the model that we selected is 3. So it means that we are using 3 regressors. So in this case, we put it here. Let's go to the signal routing and let's take the multiplexer, and with the multiplexer we add 6 inputs for the multiplexer, because if you remember, the multiplexer needs to take a number of inputs equal to the number of regressors. So let's generate, I'm going to move it a little bit here in order to have more space. Of course, it's something that you can include in a subsystem. So let's take, now at the end I will do a summary of the complete project. So let's go to the discrete and let's take a unit delay. So now we generate, as you remember, from the supervision and adaptive systems, you should remember how to design this block. Of course, the sample time is 5 seconds for each delay. 5. Okay, this is the, and this is for the input. And now I'm going to take the output of, where is the output? The output is here, Y. So Y is this one, is this one. And the input is this one. The input is, where is the input? The input is this one. Okay. Now we have, as you can notice here, this is the recursively square applied to the input and output data. So this is the, just to clarify, this is the input Y. and this is the, sorry, the output, and this is the input U. So this is the block that is used for estimating the disturbance, because if you remember, so I just put here a comment, later you can ask, recursive least square width for getting factor for disturbance estimation. This is the block that we have. And if you notice, this model, this is the recursively square with forgetting factor for disturbance estimation, because in the idea of the use of this block, it should compensate what is not the part of the data that are not described. So this block represents the model reality mismatch. So let's try to design this block here. So number of parameters 6, and of course sample time 5, and if you remember, forgetting factor 0.90, let's say 97. And then I want to complete it. I am adding one further output, which is the output estimation error, as you can see here. So we put here the parameters. And the error, as you can see here, this one is the block. So I'm going to repeat again the idea, the rationale for this design. So the idea is to use this block, this recursively square, for compensating what the part of the data that are not described by this process, by this model. And in fact, as you remember, the RX model is of order 3. So I'm designing this and fed to the model predictive control. So let's try to design again the model predictive controller. So it's something new. Let's try together. So we are repeating again the same steps that we have already. So design. Okay. So let's open the structure. And now, as you can see here, we have two inputs. One is the manipulated disturbance and the measured output. And then the sample time, do not forget to set the sample time of 5. And then let's see if import. Is trying to compile to estimate the model. Is optimizing. Okay. So we can, in the same, let's see the tuning, we put the prediction horizon of 15, the control horizon of 10, and we can check the, as we in the previous case, and as you remember, we define again the constraints. Between 0 and 100. Okay, I'm going to use these values. So export the controller. Let's say if update the block. Okay, let's go to the simulation in order to see if there is an improvement. Let's see what's happened. As you notice here, there is an estimation of the parameters of your system, and this is the output of your control system. So it's something that it can improve the process of your control. I want to show you before closing the as you can see here, there is the just want to show you the file that you have as already available in your is here. Going to open it before closing. This is the final scheme that you have, as you can see here. This is the final, is the complete scheme. Actually, I'm comparing two models, and I'm designing another controller. So it's something more complicated, it's something more. So, but this is the complete design. But so is in our case is this is the improvement of your system, of your design, and it should lead to best performances for your system, for your control system. So it's something that you need to try, or at least if you want to modify the regressors for your estimator in order to provide a disturbance estimation. So this is an example of the design of a PID controller and a model predict. So PID controller, simple PID controller, MPC controller without any estimation of the disturbance and a compensation, an estimation of your disturbance. And these represent, in some cases, it represents an improvement in your simulations.